Object-oriented programming for verification. Before discussing object-oriented programming, I would like to explain how we approach verification in general. It's all about how we generate different kinds of scenarios during simulation. Look at this. We are here to verify the DUT. To verify DUT thoroughly, we need to generate different kinds of scenarios. How we can create different kinds of scenarios? You can think of generating different kinds of packets. That's one approach. For example, you are trying to verify router. Then you can think of generating packets like small packet, medium packet, big packet, and bad packet. Bad packet means packet with error parity, CRC error. The other possible way could be we can think of creating different kinds of transactors. Transactors are nothing but Testbench components. Let's say you have driver which drives all the packets for the router. So you can think of having different kinds of drivers, like driver which drives packets to only odd ports, driver which drives packets to only even ports, and packets to only random ports. Or you can have two different kinds of drivers like AHB drivers and APB drivers, and then you can change the connection between AHB and APB. So within a driver, you can think of implementing two different protocols also, like AHB protocol and APB protocol, and based on the input packet, you can think of choosing different kinds of protocols. That's how you can configure the driver. So there are two main possible ways. You can think of generating different kinds of packets, or you can think of creating different kinds of Testbench components. These are all the two main possible ways. And based on the combinations, you can try different scenarios, and for each scenario, you will be generating coverage. That's how eventually you are going to look at the coverage value. The big question is, have you generated all possible scenarios? Have you taken the design through all possible scenarios? That's what 100% coverage means. That's how we sign off the verification. Now let's look at how we can use object-oriented programming to generate different kinds of scenarios. But fundamentally, how object-oriented programming works, you need to understand. Here, I'm planning to create different kinds of four-wheelers. So I'm going to define a blueprint called four-wheeler. I'm not thinking of luxury sedan, or I'm not thinking of heavy vehicles like buses or Volvo bus. But in general, if you look at, all of them fall in this category, four-wheeler. So in OOP, what we do, we define the blueprint. When we say four-wheeler, it will have four wheels, and then it will have headlight and other accessories. That's how basically we define four-wheeler in general. But later on, what we can do, we can create different flavors from this blueprint, like luxury sedan. In case of luxury sedan, we can think of converting the existing gear system into automatic gear system. And we can also think of increasing number of gears. We can think of increasing the horsepower of the engine. Look at this. This is blueprint, but when it comes to creating a particular flavor, what we do is we customize certain things like the power of the engine, the gear system. That's how we create different flavors like BMW or bus or Volvo. In terms of class hierarchy, this is how it's going to be: four-wheeler, and different flavors like Alto or automatic gear system or BMW car can be created from the same blueprint. All right. Now let's think of verification. In verification, how we want to apply this object-oriented programming concept. We want to define packet. The packet will have header, payload, parity, different fields. So we want to define all these fields as members. And what we want to do with members, we can define them as methods. So we define the packet as class. There is a data type called class. The class will have members and methods. Members are nothing but all the variables or the fields. Here the packet has got header, payload, parity, so all of them can be defined as members. But what we want to do with member, later on we want to display these variables, or we want to calculate parity from payload, or we want to compare two different packets. Maybe while defining scoreboard, as part of the scoreboard we want to define two different packets. We can think of defining the functionality like how we can compare the packets. This is how basically we encapsulate the definition. So the packet will have both members and methods like this. Now, applying inheritance concept, what we can do is we can think of creating different flavors. We discussed about four-wheeler, right? The blueprint can be extended to different flavors like BMW or Buzz or Volvo. Similar to that, the packet can be extended to big packet or small packet or bad packet. We need different flavors of packets. That's what we discussed during verification approaches. So this is how we can apply object-oriented programming and generate different flavors of the packets. Overall, if you look at the stimulus would be something like generating hundreds of packets. Now when I say 100 packets, 10 packets would be big packets, 80 packets would be small packets, and 10 packets would be error packets. So I'm going to define a base class called packet, and then I'm going to extend the packet into three different packets like extended class 1, extended class 2, extended class 3. Or in OOP, we call this base packet as parent class and all the extended packets as child classes. All right. Now let's try to visualize how the simulation is going to happen. We define the blueprint or base class and create the verification environment. So when it comes to creating the verification environment, we use only the blueprint definition. So then generator will use base class packet, the driver will use base class packet, monitor will use base class packet. That's how we implement. So while creating the test bench, we think of only base class. And then while running simulation only, we will think of creating different flavors. Right? So that's the best thing about object-oriented programming. So upfront, you don't really need to visualize what kind of packets you really want to generate during simulation. Just define base class. The base class will have all the fields like header, payload, and parity. So define base class and define all the components. To create all the components, obviously you need the definition of the packet because everything is based on packet. The generator will generate packet. Think of it. The driver will convert the packet into binary. The monitor has to produce the packet. The scoreboard is going to compare the packet. So everything is going to happen in terms of packet. So you really need packet definition. Look at here. At the beginning, we use only base class definition to define all these components in the environment. The complete environment is based on only base class. And to create new test case, let's say test case 1, I'm going to use extended class 1. The extended class 1 could be big packet. So for test case 1, everything is going to be big packets during simulation. And for test case 2, extended class 2, that could be small packet. So the entire simulation will happen in terms of small packets. For test case 3, the entire simulation will happen in terms of bad packets, error packets. That's how you would be able to generate different kinds of scenarios by changing the packet. So in OOP, what happens is once you create the component with base packet, base class, the same environment can work with any kind of extended classes. So you don't really need to make any modification in the environment. You are going to make the modification only in the test case. There you are going to say like which packet you want to use. You want to generate small packet, you want to generate big packet, you want to generate error packet. So you will be using different definitions, different kinds of extended classes only at the test case level. The environment is going to remain same. We will discuss this during SystemVerilog module. This is how overall you can visualize how all the test cases are going to be. Look at this. This is RTL, design under verification, and this is environment. It is reusable. The complete environment is implemented using base class. Look at this. Base class is nothing but base packet. And each test case will use a particular extended class, like extended class 1, extended class 2, extended class 3. That could be like a big packet, small packet, error packet. But the same environment is going to drive all these packets. When you say big packet, it is going to drive big packet to the DUV. When the DUV produces the output, the same big packet will come out, and then the scoreboard is going to compare big packet with big packet. When you say EC2, it is going to happen in terms of small packets. When you say EC3, it's going to happen in terms of error packet. This is how conceptually it works. So you create the environment using base class, and then later on in every test case, you change the extended class. All right. Polymorphism. As part of object-oriented programming, you can apply polymorphism to create different flavors of methods. It can be applied only to methods. Here you look at packet has got method called send. It's a virtual method. And you can think of creating different flavors for the same method. So by default, this send method generates even parity for the packet. While creating the extended packet, we are going to redefine the same method, something like this. It is going to generate odd parity in case of extended packet 1. In case of extended packet 2, it's going to generate odd parity with some delay. So you have three flavors. One is base packet. Base packet generates even parity. Packet 1, it generates odd parity. Packet 2, it generates odd parity with delay. So in this case, the send method is going to behave in multiple ways. While creating driver, I can think of creating the packet object, and through packet object, I can call the method. If I am going to use the packet class, then obviously the driver is going to generate even parity. If I am going to use the extended packet object, then it is going to generate odd parity for packet 1 and odd parity with delay for packet 2. So the driver can do three different things. It can generate even parity, or it can generate odd parity, or it can generate odd parity with delay. And that's going to happen primarily through different flavors of send method. So polymorphism is all about creating different flavors of the same method. The name remains same, only the functionality differs. Now let's look at how we can use polymorphism to generate different kinds of scenarios. By default, the complete environment will be created with base class. So obviously it's going to drive only even parity. So test case 1, even parity. But test case 2, it's going to use extended packet 1. So it's going to generate odd parity. And test case 3, it's going to generate odd parity with delay.